In Chapter 4, we're going to start talking about something called electron configuration. What does configuration mean? Raise your hand. Think about what the definition of configuration might mean. Yes, Lucas. Not changing. No. Yeah, how it's built. Good. How it's arranged. Good. So we are going to start dealing with how are electrons arranged within an atom. Okay. Electron configuration is the arrangement of electrons within an atom. It's going to tell us where do they sit. What energy level are they in? Right? We're going to be able to eventually develop an address for an electron. Right? That's kind of the goal. We're going to be able to kind of build an address of the electron. Okay, the arrangement of electrons within an atom. For this chapter, the periodic table provides us a really good kind of parallel. It provides us a really good picture of electron structure. And it's not a literal interpretation of where the electrons are located, but it gives us really good parallels. So I'll point that out as we go along. But what we're going to start looking at specifically is something called a ground state electron configuration. And all that means is that we are going to look at electrons when they are in their most relaxed state. Okay? So it says, electrons, like most things in nature, assume arrangements with the lowest possible energies, much like high schoolers, right? You want to do the thing that requires the least amount of energy. Okay? That's true. Electrons are also little mini high schoolers. Okay? They want to do the things that require the least amount of energy. Negative? Yeah, they're negative little things that fits the high school stereotype even more, right? Very funny, Parker, thank you. The states in which electrons are most relaxed is called their ground state electron configuration, and that's what we're really going to focus on. The opposite of that is called an excited state. And excited state electrons are when they bounce energy levels, and then when they fall from those energy levels, they emit light. That's a little more complex than what we need to get into at this point, but we're going to look at something called ground state. So it's when they are in their most relaxed state, very stable, all that kind of stuff. Okay? So that's what we're going to learn. You don't need to have that last bullet. It just says that's what we're going to learn. Okay? So as we start talking about electron configurations, I'm going to use this word a lot. This orbitals, okay? An electron orbital is basically a holder for electrons. It's like a pocket, okay? So electron orbitals are where these electrons sit around an atom. They have a little imaginary containment line, right? And they are called orbitals. I want you to make this little extra note too. Orbitals can only hold 2 electrons. 2 electrons, okay? Orbitals can only hold 2 electrons. I'm going to talk about a couple different things here, but I want you to be able to see what these orbital pockets look like. Okay, I know this still will seem a little abstract to you for right now, but that's okay. I promise it'll come together. The first type of orbital that all electrons go into is called this s orbital. And an s orbital is a spherical shape. Okay, it is a circular shape, a sphere. Okay, you need to know the shapes for these first two, s and p. Okay, I would draw out what an s orbital looks like and what a p orbital looks like. Okay, an s orbital is a sphere. And so when electrons are in what we call the s block, they go into the s orbital. Okay? And so what this basically means, I'm going to give you just a second and I'll kind of walk through that. So go ahead and draw out these first two and then I'll walk you through a little bit more. These two groups are what we call the s block. Okay. Nope, not what I want. Give me just a second. Nope, give me just a second.
1 and 2.
Groups 1 and 2 are called the S block. So above those groups 1 and 2, just write an S. These 6 groups over here are called the P block. The transition metals are called the D block, and the F orbitals are called, the lanthanides and the actinides are called the F block. Okay, so I want you to see the parallels between these two things. We said that an s orbital can hold 2 electrons. Do we agree?
Yes.
There are 1, 2 elements found in the s block per row, right? 1, 2. Right? 1, 2. Helium should really kind of sit over here. Right? There are 2 groups within that s block. The s orbitals can hold 2 electrons. Do you see the parallel? Yes. S orbitals can hold 2 electrons, just like the S block has 2 groups in it, right? Or 1, 2 elements per row. Yeah.
So, helium isn't part of the P block?
It really should sit over here with hydrogen. Now the P block, this is still part of the 1s group. Okay, this P block has 6. When I drew out the p orbitals, 1, 2, 3 different versions of the p orbitals, 1 electron can fit in each of these things, which gives me a total of 6 electrons in the p block. 1, 2, 3, 4, 5, 6. Okay. So if you want to go right by those orbital shapes, the s orbital can hold 2 electrons. The p orbital can hold a total of 6. The d orbital can hold a total of 10. And the f orbital can hold a total of 14 electrons. Okay. The s orbitals can hold a total of 2. The p orbitals can have a total of 6 because there are 3 versions of the p orbitals. There are 5 versions of the d orbitals. Each of them can hold 2, so they can hold 10. And there are 7 versions of the f orbitals. They can hold a total of 14.
So if they found a new element from the periodic table, they would take into account that?
It would still sit down here, but it would be part of that P block. See how that P block is unfilled? Okay, I'm going to go back 1 slide so we can look at the shapes again. Okay, let's remember, s orbital can hold a maximum of 2 electrons. The p orbitals can hold a maximum of 6. D can hold a maximum of 10 and 14. So if we go look at the shapes of the d orbitals again, here's the d orbitals. 1, 2, 3, 4, 5 versions. Each of these orbitals can contain a maximum of 2 electrons. And when you put it all together, it looks like this. Look how complicated. Right? You don't need to know the shapes of the d orbitals. But each of these versions can hold 2 electrons, which gives me a total of 10 that it can hold. Okay? So, let's look again. If I was going to label these blocks, I start up in period 1, and I say this is the 1s block, the 2s block, the 3s block, 4s, blah, blah, blah. Over here, we do the same thing. 2, 3, 4, 5, 6, 7. Why is there no 1p block? Are there any elements in the first row there besides hydrogen or besides helium? No. Okay, what do you see here that's an issue? They don't line up, right? We don't start with the 4d orbital. We start with 3d. Okay, the only thing that really has to do with is that in the 3rd energy level, there is room for the d orbitals, but it doesn't line up that way on the periodic table. So you just have to remember that it shifts down 1. Okay, so instead of being 4d, it's 3d. The same thing happens with f. They shift down 2. They should really sit here. Okay, so you'll just need to remember that shift. Okay, yeah?
So if helium is with shouldn't that first one be like 1, 2?
Well, it's in the second energy level. Here's first energy level, here's second energy level. Every time you go down a row on the periodic table, we add a shell. So I'm going to show you what that looks like with a simulator here. Okay? Here's another way to look at it. S block elements, P blocks, even though helium really should be over there. F and D. Okay? I want to show you what this looks like. Okay, so if I'm looking at nitrogen, I have 7 total electrons. And where is nitrogen located? In what block? Okay, nitrogen is in 2p, right? So in order to get to 2p, I had to fill the 1s block and I had to fill the 2s block, right? And so the way you write this is instead of writing it vertically, like in this line like we do, we write it out horizontal and we say, I had to fill the 1s block, I know there's 2 electrons there. I had to fill the 2s block, I know there's 2 electrons there. And then in the P block, where does nitrogen fit? What number is nitrogen in the P block? 2p3. 2p3. Nitrogen's the third element in that P block. Okay, so what it's saying is that it's got 2 electrons in the S block, in the S orbital, 2 electrons in the next S orbital, and 3 electrons in the P orbital. Mm-hmm.
When you get something like radium, which is like 88, would you have to count 88? Mm-hmm.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. You go all the way until you get to the bottom. Okay? Here's the way you can check your electron configurations. These numbers up here represent the number of electrons in that orbital. And so if I want to check, I need to add up these numbers, and I say 2 plus 2 plus 3 gives me 7 electrons total. Is that how many I should have for nitrogen? Yes. So you have a way to check yourself. There's no reason we should get electron configuration questions wrong. Right? There's only one right answer, and you have a 100% way to check yourself every time. Okay? We're just telling about where is our last electron for that element. Okay? And our last electron is found in that 2p block. It's the third electron in the 2p block for nitrogen. Okay, is that making sense? You want to try a couple? You guys look dead today. Let's try, maybe, magnesium. We'll do magnesium together. We'll do a couple other on your own. We'll do magnesium together, and then I'm going to maybe switch a couple of those. Yeah, those are the same. Okay. So the first thing we look at is, where is magnesium on the periodic table? It's in the what block? It's in the 3s block. We say it other way around, 3s block. And so I know in order to get there, I have to fill the 1s orbitals. And how many electrons can fit there? 2. I have to fill the 2s orbitals. How many electrons can fit there?
2.
Okay. I have to fill the 2p orbitals. How many electrons can fit there? 6. And then magnesium is found in the 3s orbitals. How many electrons for magnesium are found in those 3s orbitals? 2. Good. So then I count up my total electrons. 2 plus 2 plus 6 plus 2 equals 12 electrons. Right? That's not part of your answer, but you can use it down, to check yourselves. Magnesium's atomic number is 12, which means I need to have 12 electrons represented. Okay, yes, Joseph?
Why do we need to know the configuration if we just know that, the electrons are the same as the protons in a neutral atom?
We're going to be able to identify basically the address. We're going to find exactly what orbital is it in. We're going to be able to locate the address of a single electron. That's going to be our goal, is we want to find out where our electrons are located. Okay. So we do this. This gives us a rough idea, saying we know our last orbital is in that 3s block, but we're going to eventually be able to go in even more detailed than that.
Is there an order of which axis, the...
Right, it's going to go P, X, P, Y, P, Z. We're not going to write them out like that, but that is how it goes. And I'll show you that here when we start drawing. So there are 3 versions, and we'll be able to tell which version it's in, and we'll be able to tell what direction it's spinning. There'll be 2 different things we can look at. Okay? Yeah?
How do you know which specific element it is? And it says 3s. How do you know which?
Right. Well, how do we know if it's sodium or magnesium? If it were sodium, it would only have 1 electron in that 3s orbital because sodium only needs 11 electrons. Magnesium needs 12. Okay? So let's do, why don't you guys try silicon, Si. I don't want you to do these ones. I want you to do silicon. So it's not necessarily an odd number thing. It's about, this is the first element in the block. So there's only 1 electron in that orbital for that element. This is the second element in the block. So it would take 2 electrons in that orbital. Okay? If we're looking at the P block, when we did nitrogen, it was the 3rd element in the block, which says it has 3 electrons in that orbital. Okay? Find cobalt. All right. If we abbreviate our if we abbreviate our electron configuration, we can do it by abbreviating it with the noble gas ahead of it. So why would we abbreviate electron configurations with a noble gas? What's special about noble gases? Noble gases are group 18. What's special about noble gases? No. What's special about electrons in noble gases? Come on. It's the end of a row, what does that mean about its electrons? It's got a full shell, right? Noble gases have full electron shells. Right? So look, in our second energy level, it would have 2s and 6p, which would give me a total of 8 electrons. Everybody wants 8 electrons, right? Noble gases have 8 electrons in their outer shell. They're happy. So we can abbreviate electron configurations with the noble gas ahead of it. So let's look at calcium. Calcium is found... Okay, calcium is found by this electron configuration. 1s, you don't have to write this out, just look. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Right, that's calcium's electron configuration, agreed? What's the noble gas just before calcium? Just before argon. So argon is 1s2, 2s2, 2p6, 3s2, 3p6. Don't those look the same? Don't they look the same up to here? Yeah. So the way we can abbreviate things is we would say calcium's electron configuration is the same as argon plus 4s2.
Oh, you're going to have us do a quiz where we have to figure out.
It's the same as argon, because argon is the noble gas above calcium. So we look a row above. Noble gases, the noble gas configuration of argon is the exact same as calcium, but calcium has an extra 4s2 on the end.
Could you do krypton minus?
No, can't go minus. Okay.
What about krypton? Take away.
Nope. The abbreviated electron configuration is with the noble gas ahead of it, plus whatever's left over. Listen. Stop. If I was looking at copper, okay, let's find where copper is. See copper? 3d9. Okay, I want you to look at what I'm going to do here. For copper, what's the electron configuration that comes before?
S2.
Nope. What's the noble gas that comes before? I said that wrong. What's the noble gas? So it's still argon. Brackets, argon. But can I just do 3d9? No. I have to do 4s2, then 3d9. Because it's everything that comes after argon until we get to copper. Right? After argon, we had to get through 4s before we could go 3d. Okay? Yes?
So we did the bromine.
We did bromine. We go argon,
Okay.
4s2, 3d10, 4p5. Can you abbreviate a noble gas with itself?
No.
No. Nope. So the only noble gas that cannot be abbreviated is helium. If we wanted the abbreviated noble gas of neon, we would say helium plus 2s2, 2p6.
Yeah.
Okay?
You did.
Or is that like a sticker?
Sticker.
Like the code of the week?